So after we heard a lot about like very fluffy, very large and very low mass white dwarfs, this is much more about massive white dwarfs. And so Ken asked me to give you a full summary of what the current theoretical state of our knowledge about type 1a progenitors and explosions is. And this is, of course, a little bit ambitious for 20 minutes. So I will have to do some completely arbitrary cuts on the topic and try to tell you what I think is like kind of the what has changed recently and what we think is, at least for normal type 1As, the current kind of, at least the way I think about them and how I consider different things. So the whole summary will be significantly biased by my personal view about the scenarios. So just to keep this in mind. So actually, like the zeroth order answer for the question what type 1a progenitors are is still relatively easy because we don't know. Right? So like there's like lots of things proposed and we have looked at lots of things, but we have no actual robust observational proof of anything. So an important question to ask and to begin with is the question, what do we actually know? And if you look at like so I think these things are all completely agreed on and they're like very robust statements. So the explosion energy of the type 1a is about 10 to the 51 ergs. The ejector mass is about 1 solar mass. The composition is dominated by alpha and iron group elements, and there's no hydrogen and very little helium, if any. And so there's general agreement in the community that these are thermonuclear explosions of carbon-oxygen white dwarfs. Now, what do we not know? Or what else do we know? Like carbon-oxygen white dwarfs in isolation are just inert, right? Like nothing should ever happen to them except if you go for super exotic physics ideas that have like no observational basis really. We know that these systems can be really old, so type 1a still happen in like very old elliptical galaxies where no star has formed for many gigayears. And we know, and I will come back to this later a little bit, we know like really a lot about the populations of type 1as, and in particular they are not a single parameter sequence even. And I will come back to this in a second later, because if you think about this more, that has like quite tight constraints, at least for the dominant mechanism of type 1s. And so the general conclusion from those things is, and also there is general agreement upon, that the type 1as are thermonuclear explosions of carbon-oxygen white dwarfs in binary systems. And so somehow the companion star, whatever it is, causes the explosion of the white dwarf. So it needs to be closed binary system so that there is some kind of interaction. So what do we not know? And unfortunately, this is a quite substantial and long list. So we don't know what the mass of the primary, and here primary means the more massive if there are two white dwarfs, or the mass of the white dwarf is. And in particular, it's important to distinguish from an explosion point of view if the mass of the white dwarf is very close to the Chandrasekhar-mass or significantly below. And significantly below in this context means about 1 solar mass, plus minus 0.2 or so. We also don't know what the nature of the companion star is. So is it another white dwarf, or is it a non-degenerate hydrogen or helium-rich companion star? And we don't really know how this thing actually explodes, which in particular, like it's hard to figure out if you don't know even where to start from. And yeah. So the main problem, of course, is there's like no clear, robust observation of a progenitor system of a type 1a, where we like kind of would go back, like we can do this with core collapse supernovae. We have the explosion, we go back into like pre-explosion images of the same area and find something. We have tried this even for very nearby ones, and even if there's deep exposures, there just isn't anything that we could see. There's, for one weird 1a, there is a hint of something, and we can discuss it as coffee if you want, but it's not a normal type 1a. And what makes it even worse, there's like if there's the binary system and there's a companion star, you would expect all kinds of effects from this companion star, right? It should be around before the explosion, it should possibly be around during the explosion, and it should possibly still be there after the explosion. And none of these things have ever been detected directly or indirectly in any robust way. So they are very weak hints that can be interpreted as a sign, but they can all be disputed as well. So none of these things is robust. Okay, now for one thing that has become very clear over the last 10 years is that there is not only one type of thermonuclear explosion. We've heard about this very briefly already here at the conference also, but there's like a whole zoo of things. So this is from a review article by Stefan Taubenberger from a few years ago, and this diagram most of you will have seen for a few times already. And so this is like in a data M15 versus a maximum brightness, so a decline rate versus how bright this thing was. And so this is kind of a purely observational plot, and then there's some kind of classification how we think which things are connected. And so for a full theoretical understanding of the whole thing, what we really need to do is we need to figure out which of these different groups is connected to which kind of theoretical scenario, right? Nevertheless, it's important to emphasize that normal type 1As, so these are the things that roughly follow the Phillips relation here, are still, depending on where you make the cut, 60 to 80% or so. So they really dominate the things we see, also because they're bright. And so, but those are also among the least understood ones. So like for some of the more special ones, like the O2CX-like, for example, or like some there's some like even smaller subclasses where we actually have very good models for. But in the end, as long as we can't explain normal 1As, like the whole identification of like specific subclasses with a certain type of scenario is always very weak, because like if you can't explain the elephant in the room, then like, yeah, it's a, yeah. What's important to notice for the normal type 1As here, so first there's type 1As have you all will notice now that even normal type 1As vary a lot in brightness, and so there has to be a primary parameter in however the explosion of whatever system works that sets the brightness. And what's like often not appreciated as much is that this brightness actually correlates with host galaxy properties. So somehow some property of the host galaxy is still remembered in the explosion. Likely it's the age of the system, but so there are some correlations here. So whatever the primary parameter is that sets the brightness, it has to be some way at least partially deterministic. It can't be fully stochastic. And I will come back to this later. And there's also a secondary parameter needed, and because even if this is your first parameter, there's quite some scatter in orthogonal to the relation, and so you need at least some secondary physical parameter to explain the scatter. Also, I think, and that's an interesting topic, but metallicity is very likely neither of those two parameters. Okay, so now to the actual scenarios, and I think it's important, or like one good way to approach this is to actually not look at scenarios as one thing, but distinguish between progenitor systems, scenarios for progenitor systems and for the explosion mechanism. So progenitor systems, there are two main scenarios that are distinguished by the nature of the companion star. And for the explosion mechanism, it really mostly depends on the mass of the white dwarf. So whether you have a Chandrasekhar-mass white dwarf exploding, or whether you have this about one solar mass sub-Chandrasekhar-mass. Now, the single degenerate Chandrasekhar-mass explosion is the classic scenario you will have heard a lot about. The double degenerate sub-Chandrasekhar-mass explosion, for example, in the D6 version is what actually kind of the modern merger scenario where most of the work currently in theoretical exploration probably goes into. However, it's important to note that although these other combinations are in principle possible, the double degenerate Chandrasekhar-mass explosion is kind of the classic merger scenario from 30 years ago that's typically revisited every 5 years or so by someone who hopes to make it work again. And there's very consistent result that this doesn't work, that leads to an accretion-induced collapse. And I think it's one of the very few things where people agree, because like everyone got the same result for slightly different reasons, but it's really, that seems to be a robust result. That's also, it's in principle also possible to make sub-Chandrasekhar-mass explosions in single degenerate systems. In particular, likely if you accrete helium from a non-degenerate companion on a sub-Chandrasekhar-mass white dwarf, significantly less work than into those two has gone into this channel. In particular, ignition is like more unclear here than in this and much harder to model. Okay, so now let's like very briefly focus on these two main models. So first, let's look at the single degenerate Chandrasekhar-mass explosions. And so one attractive thing here is that we know that at least white dwarfs with a mass close to the Chandrasekhar-mass exist, and they are accreting mass. However, it's unclear if these are actually carbonoxygen white dwarfs. It's one of the main downsides of this scenario. It's really hard to explain all the constraints about the companion star. As I mentioned before, we have really not really seen any interaction, any like present, any robust sign of the presence of the companion star. And in a single degenerate scenario, it's very hard to discuss this all away. It's also the rate estimates from like various kind of observational and theoretical arguments typically come out like 1 to 2 orders of magnitude below the observed normal type 1a rate. So this is another argument against those explaining normal type 1as. However, there's like a completely different line of arguments about this from the explosion scenario side. And so for this, let me briefly introduce kind of the state how we do the kind of our classic pipeline currently of modeling type 1a explosions. And we can since starting to do this like in a kind of pipeline sense like 10 years ago or so, we can actually do quite a lot there. And in particular, we can essentially start from somewhere, like from models that really model the initial ignition. So this is for a Chandrasekhar-mass white dwarf, where you have like the simmering phase, and then like in Nonaka et al. In 2012 had this paper about where they run these like 3D simulations of the simmering phase and really looked at like how does the ignition actually happen in those kinds of white dwarfs. We can then use a different code to use this what we know about ignition and run explosions and explode the white dwarfs until the ejector all fly apart. We can then do very detailed nuclear synthesis with like hundreds of isotopes to like really get the detailed isotopic abundance of the ejector. And then we can do 3D Monte Carlo radiation transport to get synthetic observables. And those we can then compare to observations and try to understand to which degree the model can work or not. And so for these Chandrasekhar-mass explosions, I would argue we have also from the explosion side found significant problems if we want to explain normal type 1as with them. So in these kind of in the Chandrasekhar-mass explosions, the ignition the nuclear burning initially ignites as a so-called deflagration, so as a slowly moving flame. If you want to make a normal 1a, however, you need this layered structure. And so that means that you need to transition to a detonation, to a fast-moving flame at some point. And then as far as we can tell, if this transition happens, it's stochastic. And so this is has a problem with all these kinds of correlations, because that also sets essentially how bright this thing will be and so on. It's also just an important note, and we can discuss it at coffee in more detail. 3D models generally do much less well for Chandrasekhar-mass explosions than the older 1D models, because the 1D models don't include buoyancy. And so if the initial deflagration ashes rise buoyantly, they are not in the center anymore, and then the whole thing just doesn't look as good anymore. And so that's that's why people, when they compare to observations, still many people actually compare to old 1D models, but they are much less physically meaningful than the 3D models, and the 3D models are much harder to make agree reasonably well with observations. Also, there have been long arguments about specific burning products from high density burning in the center of these white dwarfs, in observations, but I would argue that there's still no robust evidence for a high enough amount of these high density burning projects that we actually need them in normal type 1As. Okay, then let's have a look at the merger scenario. And so the main one of the kind of, so there has been there's lots of good arguments that there are many double white dwarf binary systems with massive carbon oxygen white dwarfs. So we're talking about systems where the more massive white dwarf has to be of order 1 solar mass, and the secondary white dwarf still has to be 0.7 or something. So the total mass of the system has to be significantly above the Chandrasekhar-mass for this to work. And so these systems are not directly observed. There are good reasons why that's the case. They're just very hard to see, and there are good reasons to assume that they're there. But it would be like any direct constraints on this would actually be very helpful to constrain the scenario. Our current understanding of those types of systems is that the explosion is triggered by the dynamical interaction just before the merger. So it's not the old scenario where it merges and then it makes a differentially rotating remnant and something happens much later. But it's really like the explosion is triggered by the interaction because the accretion stream can become very dynamic, and in particular in the last orbit when you would disrupt the less massive white dwarf, you really have like a very dynamical situation, and that exactly ignites the more massive white dwarf. This scenario has a lot of attractive properties. For example, the primary parameter that sets the brightness is the mass of the more massive white dwarf. And so then you can actually look at all these correlations, and at least qualitatively they seem to work out. The optimistic rate estimates for how many of these binaries exist are at least consistent with the observed rate. It also explains most of the non-detections from companions. However, it's hard to make actual positive testable predictions, to confirm that this is actually the case, the main scenario. Now, so let's look a little bit more at how this works. And so this is a movie of one of these simulations. And what you see here is a 1.05 solar mass white dwarf and a 0.7 solar mass white dwarf, and they both have thin helium shells. Helium shells a few hundredths of a solar mass. And so you see how, and so we can essentially start simulating this many orbits before anything interesting happens. You see how the accretion stream slowly gets more massive and how the surface is heated up by the interaction of the accretion stream with the surface of the primary white dwarf. And then, you see how more and more mass flows over. The accretion stream becomes denser as the system shrinks. And so also the impact and how violent this impacts here increases, and you becomes hotter and hotter. And then at some point, you start a runaway nuclear burning there. You get this, this runs around, the helium detonation runs around, converges in the core, in the CO core of the white dwarf, explodes the white dwarf. Yes. One of the problems here is that essentially, the properties of the helium shell are very poorly constrained. So essentially, we treat them as free parameters in this model. So we start with a system of two CO white dwarfs, and then just put an arbitrary small-ish amount of helium on the surface. Also there, it would be really good to have any better constraints. Now, very briefly, this is this seems to be a stable, reliable explosion mechanism. It's possibly able to explain lots of properties of the population of normal type 1As. One of the problems that, or one of the one of the things that then Ken came up to make a prediction with is, so if this works exactly as I've shown you before, then the secondary white dwarf, the lower massive one, should survive and actually just move with a really fast velocity, the orbital velocity of the binary system at the time of explosion, which is typically 1,500, 2,000 kilometers per second. And so, this is what I talked about before. So Ken then went and made a prediction, like how many of these white dwarfs should be around if they explain all, like these systems explain all normal type 1a, so at least the bulk of normal type 1a. And however, the problem is, and then he went and looked in Gaia and found like one and two weird ones when he expected like about 100 or so. And so maybe up to 3 of 100 or so. And so that's clearly not enough to explain the full weight of those. And so the question is then, like, of course, there's like always enough wiggle space to just discuss them away. Like maybe they just cool very quickly. Then you don't see them anymore. They're not bright enough. But then like it would be really good to have like a positive statement here. Now, one other thing that we've just found very recently in a paper that we only put out like a few months ago is that if you look at the system again, and so this is now again the system now we start at like a much later time, just about before this ignition happens. If you look very closely, you will see again that this explodes, and then it explodes the primary white dwarf. But then we'll see that the same thing happens on the secondary. And so the secondary will also, so the shock wave will ignite the helium on the surface of the secondary. You will also have the burning running around. And then you will actually have the shock wave of the explosion of the full white dwarf hitting the secondary as well. And this will give you the same convergence point. And if you look in detail there, then it's actually plausible from the conditions where this converges that the secondary also explodes with the exact same mechanism. And so if you then just like do this, so you see this first one, then it ignites here. You see how this runs around here and how the big shock wave now runs over this. And you kind of see how this converges here. And then you get a second, like an explosion of the secondary. Now what's crucial here is now that there's like a significant timing difference. So when you look at this, like the ejecta of the primary have essentially been long gone, right? Like long in this case, like 5 seconds. But because they are like so energetic and so fast, like in 5 seconds you actually can get quite far. And so the ejecta of the secondary now expand into the very center of the ejecta of the primary. However, they contain essentially no nickel because the central density was too low to burn through any nickel. And so if you look at like how the composition then looks at the end, you see the density of so this is the density of the ejecta if the secondary does not explode. So the secondary will just sit here and like move very fast, but still much slower than the ejecta. So it should still be in the remnant when you see the remnant, at least if it's a young remnant. And so down here you see the same thing if the secondary also explodes, and here you see the kind of the composition in terms of mean A. And so you see that in the center, so you kind of like expand into the central nickel bubble and push out all the iron group elements. But you don't really change the outer parts of the ejecta. And so if you then do the synthetic observables, you see that like the explosion actually until long after maximum light doesn't look very different because you didn't change any of the outer parts and the photosphere doesn't go that far in yet. So that might be one way out to explain why we don't find that many that as Ken expected to find in Gaia. However, also the ejecta now look very different, and so it will be crucial to actually look at like late times nebula spectra where we see through the inner parts of the ejecta. And so we need to do the same kind of modeling. It's just much more complicated there, so we haven't done it yet to figure out if that actually is a valid answer or just bullshit. Okay, and that's my summary. Thank you.
Thanks, Ruediger.
You made a comment that it was hard to understand the helium ignition in the stable mass transfer scenarios. Did I misunderstand?
No, I think my point was more it's like harder to do physically, right? So like because you don't have the dynamic, it's not as dynamical, right? So you really then need to do this like slower. You need to like make a reasonably massive helium shell, and the helium shell more has to like kind of by itself become unstable. And so this is like.
So I guess my question is, we see supernovae, a rare class that clearly show helium shell detonations Abby's here, so I'm speaking for her and the ZTF team, but is that the understanding of those is, a large shell that's undergone a long convective burning phase and has become dynamical. Do you see a problem with that type of picture?
No, but I don't think it's unique for those. I think in a double degenerate system, you could do the same if you for some reason have a massive helium shell in the primary white dwarf.
So you mentioned no robust evidence for over here.
Yeah.
No robust evidence for high density burning, but then you alluded to the manganese nebular spectroscopy. So I'd be interested to hear your thoughts.
Yeah.
On that.
So this is a different point. So the evidence of the evidence of the high density burning products in the explosion usually comes from stable nickel arguments. So the question is if you look through at the center of the ejector, do you see sufficient amounts of stable nickel that you can only make this in high density burning? Because the subchandras will also have some neon-22 that will make some kind of neutron-rich elements, isotopes, and so it will make some stable nickel. And so it's really a complicated quantitative question of do you need more than what you can have in those kinds of models? And we don't have a robust statement there yet, also because the modeling of these nebular spectra is so hard. The manganese is a more general population argument, and so the subchandra. So the question is what's the source of manganese just in general in the universe? And so the manganese very likely comes from thermonuclear explosions only, or completely dominantly, and the subchandras give you slightly subsolar manganese over iron. And so it's hard to see, so you need some source that is at least significantly supersolar to explain the observed manganese in the universe. So also there, it's more like a hard quantitative question. The question is how many high density burning supernovae do you need? So Chandrasekhar-mass explosions. And so in particular, there was a paper in arXiv a few weeks ago that probably Chandrasekhar-mass white dwarfs actually have an even higher central density than we have thought so far, which would increase their manganese yields even higher. And so possibly you get away with 10% or so of Chandrasekhar-mass explosions. And in that case, they can explain some of the peculiar class, or in particular one peculiar class very well. Then that would but this is also there are very few really strong robust constraints.
I had almost the same question, so I just wanted to clarify. So we definitely do see 1As with very strong stable nickel lines in the nebular phase, and you think it's still an open question that we can get those significantly sub-Chandra?
I think that really will depend on the details of the nebula. So in the end, in the nebular spectra, it really depends on the density of the material and whether you have the radioactive stuff nearby, how strong of a line something produces. And one of the, already those things here will look very different, because here you really increase the density of the iron group elements a lot by compressing them from the inside, right? So this is a log color scale. And so I think we are far from being able to say we can't make this in subchandras, right? But that's the robust statement you really would want to do.
Thank you.
Yeah, hi, Kishore Patra from UC Berkeley. I was wondering, in the case where you have the secondary also detonate, the ejecta look very highly asymmetrical. Would you expect any polarization in that case? And
yeah.
How do you reconcile that with the fact that observationally we don't see much continuous?
So again, until long after, until whatever 40 days after the explosion or so, the ejecta actually look the same, because you really only change the very inner part of the ejecta. And all the outer parts, so this is in velocity space here, the density, all the outer parts here are essentially identical. So you would not expect any additional polarization until long after maximum brightness. So whether the sub-Chandras from any double denaturation scenarios are sufficiently low polarized that they work with the observed constraints is like a very interesting question. But so we are planning to also just get direct polarization things from this. But I don't expect this to be like drastically different. So it's very different compared to the old violent merger models, because there the timing difference is like fractions of a second, and these like the 5 seconds difference between the two explosions really kind of layers them, and that's why kind of the ejecta of the primary white dwarf are still as spherical as they would be otherwise.
Jim Fuller, Caltech. So I'm curious, what do you think is the primary factor that sets whether or not the secondary also detonates? I'm guessing a more massive secondary is easier to detonate, or have you explored that?
That's a very good question that I don't have an answer to yet. So unfortunately, likely all 4 main parameters of the system, that is like mass of the primary, mass of the secondary, mass of helium on the primary, mass of helium on the secondary, will likely be relevant. So that's quite high dimensional, unfortunately.
So on the manganese and maybe stable nickel discussion, I'm wondering if the story of something like distillation or whatever would build like a huge concentration of neon-22 at the center is true. Could the high density burning be, or that idea be misleading us? Because, you know, one solar mass going through a double detonation just has lots of neutrons to produce those same things?
Yeah, so I think that might help. Like we looked at this like a few years ago for like what was considered back then reasonable assumptions about neon settling, or like even optimistic assumptions of neon settling, and it didn't make a vast difference. But I think it's really like it's easy to revisit. Essentially, you just need to change the initial composition profile of the white dwarf before you blow it up. And those types of questions you can look at in like much more idealized, like isolated 1D models, essentially, right? And like look at how this works.
I assume you wouldn't have looked at like 20% neon, like distillation is predicting, right?
I don't remember exactly what numbers we used.
So I think we'll go with one more question before coffee break. Apologies to cut this off. I know there's a few questions.
Thank you very much. I'm Xihao Cheng from IIS. I kind of wonder, do you think there are any observable effect on the early light curve of the supernova? You mentioned that it's about 5 second difference of the explosion.
So you mean between those?
Yeah, between these two scenarios.
Yeah. So we have like in the paper we have like we show the differences, and so like essentially like it's the difference between the dashed and the straight line and the solid lines here, and like there are some minor differences, but the problem is that these differences are of order or smaller than like the discrepancies between our models and observations. So it's like very hard to make any strong statements about this. There's one kind of more robust statement about this, is that one thing that changes systematically is that the volumetric light curves become slightly broader, and the rise time becomes slightly larger. And so that seems to make these models like a little bit better in agreement with observations, but then observing volumetric light curves is also very hard, and I'm not sure how robust those measurements are.
Okay, so you're not only talking about spectrum, but also the luminosity light.
Also light curves, yeah.
I see. Thank you.
All right, let's thank Ruediger again.